The net current in the neutral of a three-phase, three-wire system is not simply the algebraic sum of the currents in the three phases. To understand why, consider a scenario where the three-phase currents are balanced. In this case, each phase current is 120 degrees out of phase with the other two phase currents. The vector sum of these three balanced currents is zero, meaning the neutral current is zero. Now consider a situation involving appliances. The current in the neutral is not zero because the appliance loads are not purely resistive. Appliances have inductive and capacitive components. These components introduce phase shifts, causing the currents to be out of phase with each other. The amount of current in the neutral is directly related to the phase shift between the currents in the three phases. Crucially, this phase shift is not constant. It changes depending on the load characteristics of the appliances. For example, when only the air conditioner is running, the current in the neutral might be 10 amps. But when the dishwasher and disposer are running and the air conditioner is off, the current in the neutral could be 18 amps. This difference arises because the phase shift between the currents in the dishwasher and disposer differs from the phase shift between the air conditioner and the other two appliances. Therefore, the net current in the neutral is the vector sum of the currents in the three phases, not simply the arithmetic sum. This vector sum takes into account both the magnitude and the phase angle of each current. Let's delve deeper into the concept of vector sums and phase shifts. Imagine each current as a vector, having both magnitude amps and direction phase angle. To find the total current, you need to add these vectors together, considering their angles relative to each other. Purely resistive loads have a phase angle of 0 degrees, meaning the current and voltage are in phase. Inductive loads cause the current to lag behind the voltage, resulting in a phase angle between 0 and 90 degrees. Capacitive loads cause the current to lead the voltage, resulting in a phase angle between 0 and minus 90 degrees. In a three-phase system, these phase shifts significantly impact the neutral current. The inductive and capacitive reactance of the appliances causes current to shift out of phase. Since the net current in the neutral is the vector sum of the currents in the three phases, we must add these currents by accounting for phase angles. The phase angles will be different and change in real time dependent on the electrical draw on each appliance. Remember, if the loads were purely resistive and perfectly balanced, the neutral current would be zero. However, in real-world scenarios with appliances, this is rarely the case. It's important to understand that the 20 amps value referenced is likely derived from a specific set of operating conditions for the appliances and their individual phase angles at that instant. The net current in the neutral will change depending on the appliance usage. If the phase shift between the currents in the dishwasher and disposer is greater than the phase shift between the currents in the air conditioner and the other two appliances, the current in the neutral will be higher when the dishwasher and disposer are running. When analyzing neutral current in three-phase systems, it's essential to consider firstly the type of loads connected to each phase, secondly the magnitude of the current drawn by each load, and thirdly the phase angle between the current and voltage for each load. Only by considering these three factors can you accurately determine the net current in the neutral conductor. Using a power quality analyzer will allow a technician to diagnose and measure all of these values. Without understanding these, one cannot easily determine the imbalance. A power quality analyzer helps to determine the individual phase angles of the appliances. The power quality analyzer can measure the voltage and current waveforms for each phase. By comparing the waveforms, you can determine the phase angle between the voltage and current. If the voltage and current are in phase, the phase angle is 0 degrees. If the current lags the voltage, the phase angle is positive. If the current leads the voltage, the phase angle is negative. It's also worth noting that the neutral conductor plays a crucial role in handling unbalanced loads in three-phase systems. Without a neutral conductor, unbalanced loads can cause voltage imbalances, potentially damaging equipment. The neutral conductor provides a return path for the unbalanced current, ensuring that each phase receives the correct voltage. Therefore, proper sizing and installation of the neutral conductor are critical for the safe and reliable operation of three-phase electrical systems. This also impacts the overall power factor of the system. Low power factor leads to increased current draw and energy waste. Improving the power factor can reduce these losses and improve the efficiency of the electrical system. There are several ways to improve the power factor, including using power factor correction capacitors and reducing inductive loads. These phase angles also must align with any backup generators for standby power to avoid issues. If the generator cannot handle the load properly, it will be underpowered. The underpowered generator will cause damage to equipment and the generator. For example, if there are multiple motors running, then the generator must be sized properly to handle the inrush current. The inrush current can be several times the normal operating current of the motor. If the generator is not sized to handle the inrush current, the voltage will drop and the motor may stall. This can damage the motor and other equipment connected to the generator. Therefore, it is important to consider the inrush current when sizing a generator for motor loads. The NEC, or National Electrical Code, provides guidance on sizing generators for different types of loads. Specifically, NEC Section 440.13 outlines the requirements for sizing generators for motor loads. This section requires that the generator be sized to handle the largest motor load plus the sum of the other loads. The NEC provides guidance and requirements for many aspects of the electrical system, including bonding and grounding. Bonding ensures that all metal parts of the electrical system are at the same potential. Grounding provides a path for fault current to flow back to the source. Proper bonding and grounding are essential for safety. The NEC also specifies the requirements for overcurrent protection. Overcurrent protection devices such as circuit breakers and fuses are designed to protect the electrical system from overloads and short circuits. These protective devices must be sized appropriately for the load they are protecting. Furthermore, the NEC requires that all electrical equipment be listed and labeled. This means that the equipment has been tested and certified by a recognized testing laboratory. Listing and labeling ensures that the equipment meets safety standards. Finally, the NEC is constantly updated to reflect changes in technology and industry best practices. It is important to stay up to date on the latest edition of the NEC to ensure that your electrical system is safe and compliant. This includes understanding the applicable regulations. Another aspect of three-phase systems is harmonic distortion. Harmonics are multiples of the fundamental frequency, typically 60 Hz, that can be generated by nonlinear loads such as electronic devices and variable frequency drives. Harmonic currents can cause a variety of problems, including overheating of equipment, voltage distortion, and interference with communication systems. To mitigate harmonic distortion, harmonic filters can be installed. Harmonic filters are designed to block harmonic currents from flowing through the electrical system. There are two main types of harmonic filters: passive filters and active filters. Passive filters use inductors and capacitors to block harmonic currents. Active filters use electronic components to inject harmonic currents that cancel out the harmonic currents generated by the nonlinear loads. Another important consideration in three-phase systems is voltage regulation. Voltage regulation refers to the ability of the electrical system to maintain a stable voltage under varying load conditions. Poor voltage regulation can cause equipment to malfunction and can shorten the lifespan of electrical equipment. Voltage regulation can be improved by using voltage regulators and by ensuring that the electrical system is properly sized. Voltage regulators are devices that automatically adjust the voltage to maintain a stable level. Proper sizing of the electrical system ensures that the conductors and transformers are large enough to handle the load without excessive voltage drop. When dealing with three-phase power, it is important to understand the different types of three-phase connections Y and delta. In a Y connection, the three phases are connected to a common neutral point. This configuration provides a phase-to-neutral voltage that is lower than the phase-to-phase voltage. The Y connection is commonly used for distribution systems because it provides a stable neutral point. In a delta connection, the three phases are connected in a closed loop. This configuration does not have a neutral point. The phase-to-phase voltage in a delta connection is the same as the phase voltage. The delta connection is commonly used for industrial applications where a high voltage is required. It's critical to also understand the concept of symmetrical components, which is a method of analyzing unbalanced three-phase systems. Symmetrical components break down the unbalanced three-phase currents and voltages into three sets of balanced components: positive sequence, negative sequence, and zero sequence. The positive sequence components have the same phase sequence as the original three-phase system. The negative sequence components have the opposite phase sequence as the original three-phase system. The zero sequence components are all in phase with each other. By analyzing the symmetrical components, you can identify the source of the unbalance and take steps to mitigate it. For instance, excessive negative sequence currents can indicate a problem with motor windings, while excessive zero sequence currents can indicate a ground fault. So, in summary, understanding neutral current in three-phase systems requires considering firstly, vector sums, secondly, phase shifts, and thirdly, the characteristics of connected loads. It's not a simple arithmetic calculation, but rather a more complex analysis that accounts for the interplay of these factors.